So this is the study guide for Chapter 2 Test in Geometry. We're just going to go through all the problems here, hopefully describe how to do each one so that there's nothing that surprises you on your test. So we'll start with the conjecture ones. So the conjecture ones give you a pattern and they ask you to fill in the rest of the pattern and then write a conjecture, which again is just stating what you believe is happening in the process. So let's check it out. We go 4 to 9, 9 to 14, and 14 to 19. And we want to figure out what's going on here. Well, the first thing to check is adding, because adding tends to go pretty easy, at least how to check it. So 4 to 9, that'd be adding 5. 9 to 14, that'd also be adding 5. And 14 to 19, that'd also be adding 5. Well, seems like we've stumbled on the pattern already here, and that's just to add 5 each time. So here, if we add 5, that'd be 24. And then here, if we add 5, that'd be 29. So the conjecture is simply add 5 each time. Simple enough pattern. What about the next one? We go 75 to 73, 73 to 69, 69 to 61, 61 to 45. Here we subtract 2, because again, check addition subtraction first. So we subtract 2, we'll see if that pattern holds. Here we subtract 4. 69 to 61, that'd be subtracting 8. 61 to 45, that's subtracting 16. So at first glance, it might seem that subtraction wasn't good, and we might want to go and check multiplication division. But if you look here, we go -2, -4, -8, -16. It looks like we're doubling the amount we subtract each time. So we go 2, then double 4, then double to 8, then double to 16. So what we're subtracting by is twicing itself each time we go down the list. So the next one would be subtracting twice as much as 16, which would be -32, which would give you 13. And the one after that would be subtracting twice as much as that one, which is 64. And that would give you -51. So the conjecture in that case, let me set my font here to be a little bit nicer. The conjecture in that case would be to subtract, whoops, not two B's, subtract twice as much as before. So you subtract twice as much as, or you can say as you did previously instead of as before. They both mean the same thing. But just because you're not doing the same thing each time doesn't mean there isn't a pattern. The pattern could be that you're changing the number you're whatever you're doing by in a certain predictable way. So in this case, we're not subtracting by the same thing, but we are subtracting by twice as much as whatever came before, and that's something we can use as a conjecture. So this is converting stuff into if-then. And the best way to try to do these is to look for the is when it's present. So like in this case, we have an is right here, and the is going to kind of separate our if from our then. So kind of think of the is as the midway point. So it says this right here, that's probably going to be our if, and this right here is probably going to be our then. So if we were to break this up, it looked like the product of two negative numbers is a positive value. So if the product of two, or sorry, if you multiply two negative numbers, because that's what it means to get the product, right? So if you multiply two negative numbers, so if you multiply two negative numbers, then it says a positive value. Well, it was talking about the product being a positive value. So then the product is positive. Positive. So if you multiply two negative numbers, then the product is positive. So again, my if part is multiplying two negative numbers. My then part is the product is positive. Because again, when it says a positive value, it was referring to the product that I was getting. So when the is present, you can kind of use the if then to help you out there, with the if being the first part and the then being the second part. But if the is not present, like in number 4 here, it says students who use the study guide do well in the test. Then you have to kind of think in terms of cause and effect. So what's the cause happening here? Well, the cause is students using the study guide. What's the effect? Well, the effect is doing well on the test. So the if part is the cause. So if this happens, students use the study guide. Then this happens, they do well on the test. Whoops. Then. So we're going to put it into that format there. If students use the study guide, then they will do well on the test. So that's the, again, breakdown of this one without the is instead of thinking about it as first and last or beginning and second, think about it as cause and effect, because there are some cases where you can reword this where the then part actually comes first and the if part would actually come second. In most cases that won't happen. In most cases when you're saying a sentence, usually you put the if part of it first and the then part of it second. But it can be swapped in certain cases. So just be on the lookout for that and just check yourself and saying, okay, what in this situation is the cause and what in this situation is the effect? Same thing for this one too, if we didn't have the is there. The cause is that we're multiplying two negative numbers. The effect is that we're getting a positive value out of it. So the cause is the if and the effect is the then. So the next ones here deal with conditionals again, and deal with the 4 different types of conditionals. So we're given a original statement. Now we also want to find out the truth value of each one, so we should probably find the truth value of our original statement first as well. So if two angles are complementary, then their sum is 90. Well, that's true. Excuse me. That's true. If two angles are complementary, their sum is indeed 90. That's the definition of complementary, so that's true. Now the inverse is taking your original statement and putting it in terms of not. So the inverse is a not statement. So instead of saying if two angles are complementary, we're going to say if two angles are not complementary, then their sum is not 90. So once again, we're going to be using our not for the inverse. Let me shorten this up a little bit so that it can be all on one line. Let's make it look a bit better. So if we have the inverse, we want to invert it. We want to negate it. So think of inverse as negation. Inverse is when you put the not in there. Now, again, to figure out the truth value, if two angles are not complementary, then their sum is not 90. Well, in order to do a false, in order to be false, you'd have to think of a counterexample. So you have to think of two angles who are not complementary, but their sum is 90. Well, that doesn't exist. If two angles are not complementary, they can't equal 90 because then they would be complementary. That's the definition. So this would be a true statement because there's no possible counterexample you can think of. There's no possible counterexample where you have two angles that are not complementary, but they still add to 90 because then we would just call them complementary. So the converse then is the flip form of the statement. So in this case, that means you're going to flip the if with the then. So this part is going to flip over here, and this part is going to flip over there. So again, usually we call this the P and the Q. So instead of going P to Q, we're going to go Q to P when we write our statement. So let's see how that's going to look. So we're going to say if, if two angles sum to 90, then they are complementary. So we have our Q part first and our then part second. So again, this is just flipping things around the center there, around the comma, I guess you could say. And then we need to figure out the truth value. So if two angles add to 90, then they're complementary. Well, yeah, that's true. That's again how we define complementary angles, that they add to 90. So this would be also true. And remember that the two verses, so the inverse and the converse, are either both true or both false. They both have their truth value kind of linked together. Now, the next one is the contrapositive. And the contrapositive deals with just simply doing both of these. So let me scroll down here for a minute. So the contrapositive is when you do both. So you flip and you negate. Or you can say you negate and then flip. It doesn't matter either way, actually. So the contrapositive would look something like, if two angles are not, if two angles do not add to 90, or you can say sum to 90, either one, then they are not complementary. So let me just change this to sum, just so I keep using the same language. So if two angles do not sum to 90, then they are not complementary. So as you can see, that's just the negated form of the converse, or you can say it's the flipped form of the inverse. I just kind of flip the inverse front to back, essentially. So if two angles do not sum to 90, then they are not complementary. We want to figure out if that's true or false. So if they don't add to 90, we do not call them complementary. Well, that's true. If two angles don't add to 90, we can't call them complementary. That can't happen. So that's a true statement. If two angles sum to 90, then they are not, if two angles do not sum to 90, then they are not complementary. There's no counterexample for that. There's no thing where you can give me two angles who don't add to 90, but we still don't call them complementary. So if you're worried about whether something's true or false, think about, is there a way I can make the if part true, but the then part false? That's how you test a conditional. You have to make the if part true and the then part false in order for it to have a counterexample, which we can't in this case. There's no way of doing that. Now, the biconditional, I'm going to rewrite this statement here, my original down there, so I can show you how to do the biconditional a little bit easier. So the biconditional is a little bit tricky. So our original statement would be, if two angles are complementary, then they add to 90. So that's our original. I put here original. The biconditional, I'll just put bicondi for short. The biconditional is when you drop the if and replace the then with the if and only if. So the biconditional requires us to drop the if part, drop the if, and just say, instead of saying if two angles are complementary, we just say two angles are complementary. And then instead of saying then, we replace it with if and only if they add to 90. And let me reduce the font here just so it doesn't bleed over into our other spot there. So if two angles are complementary, then they add to 90 is our original statement. So to do the biconditional, all you do is you cross out the if and just start directly from there, and then replace the then with if and only if. So you replace the then with this part right here. Now, the way a biconditional is meant to be made is that it should be true both going forwards and going backwards. So two angles are complementary if and only if they add to 90. That's true. There's no other way I can talk about angles being complementary unless they add to 90. So if this part's true, if they're complementary, then they add to 90. That forward version is correct. That's basically our original. Then it should also be true backwards, which means that if two angles add to 90, then they have to be complementary. Or you can say two angles add to 90 if and only if they are complementary. So I should be able to read this backwards or do this backwards and also get a true statement. So two angles add to 90 if and only if they're complementary. Well, that's also true because that's just our converse. So the way you can check a biconditional is that if your converse and your original statement are both true, so if your original statement and your converse are both true, then your biconditional has to be true, which in this case it is. Because all your biconditional says is that it's true going this way and it's true going this way. If you can read a biconditional both forwards and backwards and have a true statement both times, then the biconditional is considered true. If it's false in just one direction, so if the forward direction is false, or if the backwards direction is false, or if both are false, then the biconditional is false itself. So let's go on here to laws of deduction. So there's two main laws of deductions that we have, law of detachment and law of syllogism. So law of detachment deals with this when there's only one if statement. So what you can do is, if you're going to be confused about it, if there's only one if statement in your setup, you can automatically assume that you may be using law of detachment. So you can go ahead and write that in there, and then if for some reason you can't draw a conclusion, you can just cross it out. So this one says, if two lines are parallel, then they do not intersect. Okay. Lines x and y intersect. Well, that really doesn't give me much to go on. Because again, if we do this in PQ format, so if two lines are parallel, P, that leads to the fact that they do not intersect, Q. It says lines x and y intersect. Well, that's not either P nor Q. That doesn't help me out in any case, because this is the only thing, this is the only tool I can use right now. So this would be like something like not Q. Remember, the squiggly means the opposite. So Q says lines do not intersect. This says lines x and y do intersect. So this gives me not Q, and it says, okay, now that you have not Q, what can you tell me? Well, I can tell you nothing, because all I know right now is that if you have P, I can give you Q. You've given me the opposite of Q, therefore I can't give you anything. So this actually would draw no conclusion, because they don't give you the correct setup. Now, since it's no conclusion, by the way, that means this doesn't work. So you can just cross that out. If they had said lines X and Y are parallel, so if they had said this, if they said lines X and Y are parallel, then I would have my P statement satisfied. It says if two lines are parallel, X and Y are parallel. Well, that's true. So then I can conclude that lines X and Y do not intersect. So since they gave me P in this case over here, since they gave me P, then I can conclude that Q works. And that would be by law of detachment. So this would be a valid conclusion here. Lines X and Y are parallel, so that's satisfied. Therefore, they do not intersect is what I can conclude. But here they gave me the opposite. Here they gave me the opposite of my conclusion. Therefore, I can't say anything about the situation. So there's no conclusion to be made here. Number 10 deals with when you have two if statements. And if you have two if statements, that means that your law is going to be, if it's going to work, law of syllogism, or also known as transitivity. Transitivity. Or syllogism, as I believe it's called. I probably misspelled that, so that's my mistake. So if you have two if statements, this is the law that would be used. So let's see if it's actually going to work this time. So if it's rainy, then the street will be lit. So let's label this P goes to Q. If the street is wet, then driving will be dangerous. Well, we already have the street being wet here, so this is another Q statement, just in the if part. So street will be wet here, street will be wet here. So Q, driving will be dangerous. I don't have a variable for this, so we'll just use R, because I've already used P and Q, so might as well use R. And let's see what we can deduce from this. So we have, the first one says P goes to Q. The second one says Q goes to R. Well, from that, if we have Q ending here and Q starting here, we can basically cross out the middleman and just say P goes to R. So these are our three valid conclusions. These are the three things that we can deduce from this problem. Now, the problem is that this one and this one are simply restating the ones we got. So we don't want to rewrite these, because that wouldn't be really drawing a new conclusion. That's just restating something that's already been given to us. We want to figure out, how can we say this? What can we say about that? Well, let's check here. If it's rainy is P, street will be wet is Q, driving will be dangerous is R. So once again, just like I did here, I can go ahead and cross out the middleman, because I have street being wet twice. So I can cross that out and simply go P to R. So I can link up these two here. So I can say, if if it is rainy, then driving will be dangerous. Dangerous. And let me draw a little bit of a barrier here so we don't get confused about what's what. So if it's rainy, then driving will be dangerous, and that is a valid conclusion. That is P to R. We want P to R, so this is the correct law to use. We would be using law of syllogism or transitivity. I believe the O goes before the G, so that's my mistake there. I am not the best speller in the world. So when you have two if statements, this is the law that should come to mind. And this only works if the end of the first one is the beginning of the second one. If the first statement was flipped around and said if the street is wet, then it's rainy, if that's how they state the first one, then I couldn't use this because it has to go diagonally. The ending of the first has to be the beginning of the second. Keep that in mind when you're doing law of syllogism, or also known as transitivity. So the next one's just kind of a knowledge check here. Deductive reasoning is based on blank, where inductive reasoning is based on blank. Well, deductive reasoning is based on logic and rules, or you can say facts. Let me just type that in there rather than try to write it with my pen. That'd probably be easier. Let's do 24. See if I can squeeze it in here. So this is based on logic and rules, whereas inductive reasoning is based on many examples. So inductive reasoning is when you have a bunch of examples back to back to back to back, and you draw a conclusion from that. Kind of like the first problems we did. If we jump back a little bit, this stuff right here was inductive reasoning. We used past examples to predict what's going to happen in the future. Just like here, we use past examples to predict what's going to happen in the future and create a law or a conjecture from it. So that was inductive reasoning because it was based on examples. Deductive reasoning was like what we did here. We didn't use past examples because there were none. We just simply used a rule that we knew was true, and then we tried to apply it to the statement they gave us. Or like here, we used two rules we knew were true, and then figured out what we can deduce from that. So deductive reasoning is based on logic, rules, or you can say laws, because we tend to call them laws, whereas inductive reasoning is based on examples. So the proof sections here. The first one's an algebraic proof, and as we know, we always start our proofs with our given. So we'll say 2x plus 5 times x minus 6 equals 4x plus 12, and that is by given. So always start with our given, and in an algebraic proof, we just simply solve the equation and then write our reasons as we go along. So the first thing I'd probably do is get rid of this parentheses by, again, if you don't know, multiplying the 5 to both numbers on the inside. So I'd say 2x plus 5x minus 30, 30, is equal to 4x plus 12, and that is by distribution, or distributive property, if you want to call it that way. So now that we've distributed 5x, I would go ahead and combine my like terms. So I would combine these two values there. So we'd have 7x minus 30. Can't find my 0 key. 30 is equal to 4x plus 12. And that is by combining like terms, which we normally call simplify, or simplifying if you want. So if you say simplify or combine like terms for this reason, that'd be okay either way because they both mean the same thing. Then next, I would actually subtract 4x from both sides. So I like to move my x first rather than my non-x, but it's up to you. Make sure you don't move them both because, again, you want to make sure that you do one step at a time, not too many at once. So you subtract 4x from both sides, and you get 3x minus 30 is equal to 12, and that is by subtraction, POE. And then now you can take care of the 30, so you can add 30 to both sides. So once again, you don't want to do too much at once, otherwise you're liable to skip steps, and that's going to be no good. So now you have 3x equals 42. Let me move that over a little bit so it's more in line. and that is by addition POE. And then lastly, hopefully you can see that we're going to divide by 3. And that's going to give us our ending result of x equaling, do some quick mental math here, that the 42 divided by 13 would give us 14. And that would be by division, POE. Now, there is some room here for you to put your own spin on things, so you might be able to do it in one step less or one step more, depending on how you broke down your work here. But this is a pretty standard way of doing it. And again, it's just do the algebra, give the reason. Do the algebra, give the reason. Do the algebra, give a reason, all the way down. And just make sure you're only doing one step at a time. Now, for example, here, if you're combining like terms on the left and right in one go, then that's okay because they share the same reason. But basically, if two items do not share the same reason, do not do them at the same time. So here I subtracted and then added. So I didn't do them at the same time. I did subtraction first, wrote my reason, add second, wrote my reason. So the geometric ones here we have to fill in. So it says D is the midpoint of CE, and it says DE is half of CE. That's what we want to prove. So it says D is the midpoint of CE here. Well, our first reason is always given. That's no big deal there. Then it says CD is equal to DE. So CD, this one right here, come on, there. So CD is equal to DE. That's what they're deducing. Well, how can they say that this half is equal to that half? Why is that true? Well, it probably has something to do with the fact that D is the midpoint, right? If D is the middle, if this is the middle right here, that means the first half has to equal the second half. That's the definition of a middle, or the definition of a midpoint, which is exactly what we would use here. We'd say, by definition of midpoint, because that's what a midpoint does. That's the purpose of it, is to cut a segment in half, and so that your first half is equal to your second half. So we say definition of a midpoint. And again, if their given has a midpoint in it, if you're given that something is a midpoint, you're probably going to use definition of midpoint pretty early on in your proof. So then he says, and this is a little bit tricky one, he says CD plus DE is equal to DE plus DE. Now you might think segment addition at first because you're adding segments together, but look closely. We added the same thing to both sides of this equation. So we started here, and he just added DE to both sides. So this is not segment addition. This is actually just simple addition property of equality. Because we're taking an equation, we're taking this equation right here, and we're simply adding DE to both sides of it. So we're not adding two new segments to get a bigger segment. It's not like CD plus DE is a new big segment. It's just simply adding the same thing to both sides. It's not a number, but it is still the same thing. And then down here, we're just combining like terms. So DE plus DE is 2DE. So this is just combining like terms, or as we can call it, simplify. And then they go to CD plus DE is CE. So once again, we have to think carefully here. This is saying that if I take this segment here and add it to this segment here, I get the entire segment in total. CD plus DE is CE. Well, that is almost verbatim the segment addition postulate, because I am adding two segments to get a bigger segment. So kind of notice for a minute the difference between step 5 and step 3. In step 3, we have an adding on both sides. In step 5, we're simply saying this segment plus this segment is this big segment. So that's why this one's segment addition, whereas this one's just addition. Because this deals with adding two things to get a larger thing. This just deals with adding one thing to both sides. Then this says 2DE equals CE. Well, this is a clear-cut substitution. And to show you why that is, we have the same thing here. So we have this sum here, and we also have that sum here. It's the same thing. So if these two sums are equal, which they are because they're the exact same thing, then that means that these two items have to be equal to each other as well by substitution. So if those two things are equal, that means that these two things have to be equal, which is what they did there. They just simply said 2DE is equal to CE, because substitution says that I can swap them out. Or another way of thinking about it, if you don't like thinking about it that way, because you could also maybe use transitive in that case too, is you can think about it as they simply took 2DE and swapped it in for this. They just took this out and put 2D in, 2DE in, sorry, because it's just the same thing. We already know that this is equal to 2DE, so we can replace it. And then they ended with a division property of equality, because again, this might be hard to see if you're not used to doing the fractions, but they simply divided both sides by 2. So they divided this by 2, and they divided this by 2. So instead of saying CE over 2, they just said, okay, well, if this is 1 CE, then I'm just going to say it's 1/2 of CE when I divide it by 2, because anything divided by 2 is simply saying 1/2 of it. So for example, if I take x and I divide it by 2, that's the same thing as saying 1/2 times x. If you don't believe me, we can do a quick little mental check here. 10 divided by 2 is 5. And then if I take half times 10, I also get 5. That is a 5 there, by the way. I have a tendency to close my 5s too much. So these two things are the same, which means that dividing by 2 and timesing by a half is the same. So they just wrote it in a different way. So again, the main thing here is don't get tripped up on addition POE and segment addition postulate because they look very similar at first. But again, segment addition postulate is 2 things or more add to 1 thing, whereas addition property of equality is you add the same thing to both sides. For the angle one here, this might look complicated, but it's actually one of the easier ones once you work through all the minutia. So we're given that 2 lines act as bisectors, and we want to prove that JKM is congruent to NKL. So we probably don't even have to look at this, but we always start with their given, and that is true. KM bisects JKN. But if you notice, that's not the only given we had. We have this part right here, but that's not in the first statement. So if we look down a little bit, we see that that is right there. So this second half of the given is right here in step 3. So we can also jump down from it and call this given as well. And this doesn't happen often, but it is legal to split up your givens like this. You don't necessarily have to use all your givens at once. Now, again, if they put this on step 1, it would be just as fine, but they just decided not to. So here, we have JKM is congruent to MKN. So JKM, which is this one right here, is congruent to MKN, which is this one right here. And we know from the top here that KM bisects JKN. So here's JKN, here's KM. So we know that this is a bisector. I'll put a little capital B here for bisector. This is a bisector. And we know, at least we should know, that when you have a bisector, if you look at your theorem bank, it cuts an angle in half so that both angles on either side, which would be this angle and this angle, both angles on either side are equal. That's what a bisector does. That's the purpose. So this would be by definition of bisector. Because again, we use bisectors to prove 2 angles are congruent, and it has to have a bisector given for us, which it does. It says KM is our bisector. So just like with midpoint, if they give you that a line or a ray is a bisector, you're probably going to use definition of a bisector pretty early on in the proof. And as you can see here in step 4, that's also a very similar case. We have MKN, which is this one right here, is congruent to NKL, which is this one right here. And again, it also says that KN is a bisector of MKL. So KN, which is this line right here, is also a bisector of NKL, which also means that this angle right here and this angle right here on either side of the bisector are congruent. So we can use the same reason, by definition of bisector. So now we're saying that JKM is congruent to NKL, and this is where you have to kind of look for a limit and say that, okay, I have JKM equal to MKN, and I have NKL also equal, or congruent I should say, to MKN. Well, if this is equal to MKN and MKN is congruent to that, then that means that the two original things have to be equal or congruent to each other. And that's a clear-cut case of transitivity because you have three congruencies going back to back to back. So transitive property. If you want to put POE, you can as well. Actually, it'd be probably POC because it's a congruency, but either way is fine. So that would be how this proof goes. And again, it looks like it's redundant because it is, but that's because you have two bisectors. So we went, given the bisector, definition of bisector. Given the bisector, definition of bisector. And then once we got that out of the way, we saw that we have a case of transitive property here because we have the same angle twice, and we have two different angles equal to it, or congruent to it. So that means that these two angles have to be congruent to each other. Because once again, you can just think of simply cutting out the middleman, so cutting out that angle, cutting out that angle, and you're just left with these two together. So the last little bit here is just property recognition. So we want to figure out what's the property that justifies each statement if it was used in a proof. So if in a proof you saw this statement, what property would you reason that would be? Well, it says AB equals AB. So the length of AB is equal to the length of AB. Well, if something's equal to itself, that's what we call reflexive. It's where you get kind of the word reflection from. So reflection is you're looking in a mirror. You're looking at the same thing back at you. Well, that's the same thing here. AB is reflecting itself and getting AB back. So we call it reflexive instead of reflection. So reflexive property says that the same thing is equal to itself. So A equals A, B equals B, 1 equals 1, 2 equals 2, X equals Y, triangle equals triangle. If you just have the same thing equal to the same thing, so pumpkin equals pumpkin, that's a reflexive property. Same thing equal to itself. If B is the midpoint of AC, then AB equals BC. So let's look at this happening here. So we have A, B, and C. Sometimes it's helpful to draw a diagram to figure out what's going on. So it says, if B is the midpoint of AC, then AB is equal to BC. Well, it says here, if B is a midpoint. Well, what do we normally do if we have something being a midpoint? Well, we just call it definition of a midpoint. So usually this is almost a given statement, but the logic behind it is the definition of a midpoint. Because their main focus is on the conclusion. So we're saying, if this is true, how can we deduce this? How do we know that that's true? Well, we know this is true by the definition of a midpoint. Because we know the definition of midpoint is true. It's a definition. We know it's true. So therefore, that this case happens leads to this case by definition of a midpoint. So that's what a midpoint does, is it cuts a segment in half so the first is equal to the last. That's its purpose, therefore it's its definition. If xy equals AB and AB equals ZW, then xy equals ZW. So how can we conclude this? What's the law that goes with that? Well, this is a case where you have three things. Whoops. You have xy, you have AB twice, and you have ZW. Well, once again, you can cut out the middleman, and you're left with xy and ZW. And that is transitive property, because you have three things going on. You have one acting as your base. So AB here is acting as our base segment. It's what xy is equal to, it's what ZW is equal to. So we cut out that middleman, and we get our two original segments, which is transitive. So again, if you have three sets of equal signs, so 1, 2, 3, that's usually going to lead you to transitive property. And then number 4, if x is between wy, then wx plus xy equals wy. Well, again, let's draw that out here real quick. So now it says between, it doesn't say in the middle, so I'll try not to draw it too much like it looks like in the middle. So here's w, here's y, and it says x is between them. So x would be something right here. And what this thing says is that if we take wx and we add it to xy, we get our entire length, which is wy. And how do we know that's true? Why can we conclude this? Well, once again, if you look at what's happening here, you're adding a segment to another segment to get a bigger segment. Well, that's what we call segment addition postulate, because you're adding two things to get a larger thing. You're adding two pieces to get a larger piece, and that is by definition the segment addition postulate. We don't say definition of segment addition postulate because the postulate part takes care of that fact, so we just say segment addition postulate rather than too many words there. And again, you can look in your theorem bank if you have one, to kind of see how you can get these as well, because the conclusions are what you're looking for in numbers 2, 3, and 4. So you're looking for, how can I deduce this conclusion if this was my given statement? And the reasoning would be the segment addition postulate. So that's it for this study guide here. I know it was kind of a lot of information. This chapter is very, like I said, vocabulary intensive. So those of you that don't like vocab or English or stuff like that might have a little bit more difficult time, but it will get better over time as we practice throughout the year. So I hope you enjoy the video. Have a good day.